Hey there, space-curious friend. Picture two asteroids out in the dark, about as far from Hollywood explosions as you can get. One of them is quietly lobbing what scientists are calling cosmic snowballs at the other. Slow, gentle clumps of rock drifting across a gap wider than an entire city block. And believe it or not, the whole snowball fight is powered by nothing more than sunlight. Here's the thing. When NASA slammed its DART spacecraft into the moonlit Dimorphos last year, the team expected a clean, one-and-done impact. Instead, the encounter revealed something bigger. Dimorphos and its larger partner Didymos are already in the middle of a long, slow material exchange. More like neighbors passing tools over a fence than lonely boulders floating in space. First signpost, why we care. Those drifting clumps aren't space junk. Their sizes, their speeds, even their flight paths give away secrets. How loose or compact the surface is, how often the terrain gets shuffled, and how these bodies may evolve over decades. It's as if we walked into a crime scene and the fingerprints were still hanging in the air. Second signpost, what DART really saw. Zoom in on those faint streaks in the final DART images. By tracking how their brightness changes from frame to frame, researchers can estimate density. Does the clump act like dusty powder or a cluster of sturdier pebbles? That, in turn, tells us how fragile the surface might be when a future spacecraft, or a natural impactor, pokes at it. The geometry of each streak is another clue. If many streaks point back to the same longitude or latitude on Didymos, that hints at weak zones, low spots where grains collect, or ridges that rotation slowly pries apart. Over time, these preferred launch pads could build equatorial ridges, expose hidden boulders, or carve shallow troughs without a single Hollywood-style collision. Let that sink in for a second. Third signpost, why this matters beyond one pair. Because Didymos and Dimorphos are close enough for us to study in detail, they're now a template. When telescopes pick up odd brightness swings or color shifts in distant asteroid pairs, astronomers can ask, are we witnessing the same slow trade in surface grains? And then there's planetary defense. A world that's constantly rearranging its skin will absorb or deflect an impact very differently from a solid chunk of bedrock. The thickness of that mobile stuff, how easily it floats away, even how much of it sticks around in orbit, all of that changes how much push you get from a kinetic smack. Lessons from DART will guide where to aim, how hard to hit, and whether a gentle nudge might sometimes beat a big shove. Mini story break. Think of a glacier back on Earth. It grinds over bedrock, ferries stones downhill, and hides older scars under fresh layers of ice. Our asteroid pair is doing something similar, only the ice is drifting grains and mini boulders. The surface gets a constant makeover. What looks brand new might just be freshly dusted. Or picture a construction site. Dust from one area keeps settling onto newly painted walls across the yard. Check those walls years later, and you could easily misread which coat of paint came first, unless you knew how the air currents moved. For asteroid explorers, the air currents are sunlight, rotation, and gentle gravity games. Fourth signpost, implications for future missions. Surface age on these little worlds may feel more like fashion than geology. That complicates everything. Dating craters, reading color differences, even choosing a safe landing spot. A lander might sink into fresh grains in one place and hit firm ground a meter away. Upcoming missions may need dynamic maps that track not just where rocks are, but where they're drifting next. Big picture pause. In the long run, these slow trades turn a simple impact test into a living laboratory on how rubble worlds age. If small bodies are this restless, future explorers may have to treat orbits like hiking trails after a storm. Paths to be checked, recharted, and maybe even groomed as the terrain keeps moving beneath them. Personal challenge. Before next week, ask yourself, how could you rehearse for impact in your own life the way DART rehearsed for deflecting an asteroid? Pick one specific risk, career, financial, environmental, and run a small test now instead of waiting for crisis. And think about the quiet snowballs you're already throwing, the tiny, repeated habits that may, over months or years, nudge your life or your community onto a totally different path. Do you like that trajectory? Exceptional recap. So here's what we covered today. 1. Two asteroids, Didymos and Dimorphos, are locked in a cosmic snowball fight, trading material thanks to nothing more than sunlight and gentle gravity. 2. DART's camera caught those snowballs mid-flight, turning a one-time impact into a treasure trove of data on surface strength, density, and weak zones. 3. This slow exchange helps us decode brightness oddities in far-flung binaries and, crucially, fine-tune how we might defend Earth from a future threat. 4. The find rewrites how we measure age on small worlds. Fresh-looking surfaces might just be newly dusted, not newly formed. 5. Finally, it's a reminder for all of us. Small, consistent actions, whether in space or in life, can shift big trajectories over time. Take that knowledge, do something experimental with it this week, and keep looking up. The universe is busier, dustier, and far more dynamic than it first appears.